So let's continue with continuity and studying continuous and uniformly continuous functions. So the first question which we're going to think about now is the function f of x equals 1 over x. The graph of this function is something like this. And the domain of this function is r minus 0. And the range of this function is also r minus 0. Now, this function is continuous. So f of x is continuous. Do you all agree that f is a continuous function? Or do you think there is a discontinuity? Or do you think f is not continuous at 0? So maybe it's better to phrase it as a question. So rather than just writing it, maybe it's better to state it as a question. Is f of x equal to 1 over x continuous or not? I would like to hear your answer. So tell me, what do you think? Okay, Richard says it's discontinuous at 0. And I think for obvious reasons, right? Because if you just look at the graph of the function at 0, it looks discontinuous. It doesn't look continuous there. So one person says it's discontinuous. Any response to that? Do you all agree? Is this answer correct? Okay, so let me tell you, yes, William, that's what I wanted to say. The point is that when we have a function, so both of you are correct. So in some sense, all of you are correct. There's just one thing we should really note, and that's the fact that when we have a function from A to B, it means the domain is A. It means function is defined on A. When we say a function f is continuous, it means f is continuous at every point. At every point x. But every point x where? Every point x in our domain, right? Every point x in our domain, which is A. Do you all agree that that's what we mean by a continuous function? It means it's continuous at each point in its domain. So when I'm talking about the function f of x 1 over x, when I'm saying this is a continuous function, what I really mean is that it's continuous at every point in its domain. 0 is not even in the domain of the function. So it's not even defined. The function is not defined there. So it really doesn't make sense to even ask if f is continuous or discontinuous at 0. It's kind of like asking if f of x equals square root of x as a function which is from 0 to infinity to r. It's like asking if this function, if it's continuous at, say, x equals -1. This doesn't make sense. In the same sense, it doesn't make sense to say this is discontinuous at 0. So the domain is r minus 0, and when I'm saying this function is continuous or not, I really mean on its domain. And and then it means it is continuous because 0 is not even in the domain. So is it clear to everyone? Is there any question in this regard? Okay. Okay, so let me erase. So f of x equals 1 over x as a function from r minus 0 to r minus 0 is continuous. Now, we can think about this function f as a function from interval, open interval, from 0 to infinity to, again, open interval 0 to infinity. And again, of course, it is continuous. It's a restriction of a continuous function to smaller subset, and therefore it is continuous. Now the question is that if this function is also uniformly continuous, is f on this interval, on the interval we defined here, on this interval, is f uniformly continuous? So I'm not rewriting the domain and range here, but f as a function from 0 to infinity to 0 to infinity. Okay, think about that for a few seconds and see if you can prove if you can prove it's uniformly continuous, or you can show it's not. Okay, William says no. Why? You can unmute yourself and explain if it's easier for you to explain rather than typing. Okay, I can hear you, William. Why do you think it's not uniformly continuous? So in the meanwhile, I'm going to just write the definition of a function f being uniformly continuous. We would say f from here, from 0 to infinity to 0 to infinity, is uniformly continuous, if for any positive epsilon there exists positive delta, such that for any 2 points, x and x prime, of course in the domain of the function, which here is 0 to infinity, such that the absolute value of the difference between x and x prime is less than delta. That would imply the absolute value of difference between f of x and f of x prime is less than epsilon. Okay. Okay, I can hear your answer now if you want to say anything. Well, no, you can just explain why do you think this is not uniformly continuous. I don't really want a formal proof, but you should have a reason, right?
Yeah. Sorry. So what it means to be not continuous is that if you can find 2 points that's less than delta, and you find that f of x minus f of x prime is greater than or equal to epsilon, then it's not uniformly continuous. But in this case, I haven't found out what delta was and what y was, so that's why I'm a little bit worried about saying it's not uniformly continuous.
Mm-hmm.
I do know it's not uniformly continuous, though.
Mm-hmm. Yeah, so, okay, I can explain a little bit more. So here the point is that, okay, I can mute you for the second. So the point is that when we are thinking about functions which are uniformly continuous, usually the way to think about it is how fast they grow, right? So look at this thing. It says if x and x prime are close to each other, if they're close enough, then the values of the function at x and x prime are also close. The values are also close to each other. Okay? So in some sense, it means if the input, if 2 points in the input, so this is the domain of the function, say schematically, this is A, this is B, this is domain, this is range, and this is F. If 2 points in domain x and x prime are close to each other, the values of f and f of x and f of x prime should also be close to each other, right? That's what it means. So for example, here for 1 over x, this is not really true. Look at the graph of the function. So if I take these 2 points, x and x prime, they are pretty close to each other, right? If I look at the f at x and f at x prime, this is f of, say, x, this is f of x prime. They seem quite close to each other too, so it seems fine. But what if I choose x and x prime here? Same distance, x and x prime. So if the difference between x and x prime is delta, say difference between this new set of pair of points, x and x prime, is again delta. Now, if you look at f of x and f of x prime, this is going to be f of x prime. This is going to be f of x. So here, this is going to be the difference between f of x and f of x prime. And as you move x and x prime towards 0, even if you kind of keep x and x prime close to each other, the difference between f of x and f of x prime will become huge, right? So in some sense, x and x prime are very close to each other, but f of x and f of x prime are not close to each other anymore. That's why when we are getting closer and closer to 0, we can see the function f of x equals 1 over x is not uniformly continuous. That's the informal answer. That's the kind of intuitive idea. If it's clear for everyone, I can start to write the more formal proof. Does it make sense to you? Okay. Okay, so let's try to write a more formal proof of this fact. So we want to, more rigorously, we want to prove f of x equals 1 over x as a function from 0 to infinity to 0 to infinity is not uniformly continuous. So suppose it is. So proof by contradiction. Suppose it is. It means for any epsilon positive, there exists delta positive, such that if 2 points x and x prime are closer to each other than delta, then f of x minus f of x prime are closer than epsilon. Okay. So let's choose some epsilon. It should be true for any positive epsilon, right? We're assuming it's proof by contradiction. We're assuming it is uniformly continuous. So we're assuming this statement holds for any epsilon. Let me take epsilon to be 1. Because it's correct for any epsilon, I can choose this specific epsilon. right? We want to say there exists positive delta. Suppose there exists positive delta. So we are assuming the statement is correct. So there exists a positive delta such that if these 2 points are closer than delta, then f of x minus f of x prime, their distance is less than 1. Okay. So if x minus, so we are assuming the distance between x and x prime is less than delta. So for example, x prime can be x plus delta over 2, right? So for example, maybe it is not logical inclusion. I can say for example, if x prime is x plus delta over 2, then x prime minus x is delta over 2, and delta over 2 is less than delta, right? So I can take x prime to be x plus delta over 2, right? So epsilon is equal to 1. I have some delta. I have x prime equals x plus delta over 2. The statement should hold for these numbers, right? F of x is 1 over x. F of x prime is 1 over x prime, which in this case is 1 over x plus delta over 2. Now let's look at f of x, the absolute value of f of x minus f of x prime, which is supposed to be less than epsilon, which in this case epsilon is 1. So here it's gonna be 1 over x plus delta over 2 minus 1 over x, the absolute value of that. This is equal to x times x plus delta over 2, delta over 2. Right? This is the absolute value of f of x minus f of x prime minus. And as we said, this is supposed to be less than epsilon, which here is 1. It means delta over 2 is less than x times x plus delta over 2. Now, is this thing always correct? Now, this should be correct for this. Should be correct for this. Should be correct for any x in this interval. But is it correct? Look at this equation, this inequality. Is it correct for any x, any positive x, or not? Why? Okay, Nick says no. Why is that? Well, not necessarily when, okay, he says when x is less than 1, this is not correct. You are right, but we need kind of give a reason. It might be correct for some numbers less than 1. But the point is that, well, no, okay, and I got another answer which says because x can be as big as we want, the point is actually the other way around, because x can be as small as we want. So let me erase some of these so we would have more space. So, okay, so after all these computations, we got to this point that delta is a fixed number. This is a fixed number. And we are saying it's less than x times x plus delta over 2, where this is, it can be any number, any positive number in this interval 0 to infinity. The point is that x can be as small as we want. Well, as a positive number. So for example, we can send x to 0, right? Because, well, this is the interval 0 to infinity. X can be any positive number. We can send x towards 0, which is still positive. What would be the limit of this thing if x goes to 0? Well, obviously the limit is 0, right? Because this would also converge to 0, because it's x times x plus delta over 2. If x is going to 0, it would be 0 times something else, a finite number, therefore it's going to be 0. And it would imply that delta over 2 is less than 0. But is it correct? Delta is a positive number. How can a positive number be less than 0, a negative number? This is contradiction. Contradiction. And therefore, f of x equals 1 over x is not uniformly continuous when we understand f as a map from 0 to infinity to 0 to infinity. Any question? Okay, so as I explained this in another example in the previous meeting, being uniformly continuous doesn't only depend on the formula of the function, but it also depends on the domain that the function is defined on that domain. So my next question is this. If I think about the same function f of x as 1 over x, but this time as a function from 1 to infinity to r. Now, so we made here, I made the domain smaller. Is f uniformly continuous or not? Either disprove or prove it. Or so here, either you should prove it is uniformly continuous or you should show it's not. Okay, you can tell me what you think. You can think about that for a few minutes. Okay, in the meanwhile, let me ask you something, guys. Do you feel you're learning through this online meetings? Does it feel good enough for you? I mean, we didn't have much experience for these courses to have online meetings. You can unmute yourself now. We can discuss it. I'm interested to know how it's going, if it's going well or not.
Yeah, it's going well. Really appreciate the videos. That's pretty much the good part about it, the videos, and you can go back, watch some stuff if you miss something. But something that there's no downside, in my opinion.
Yeah, but we are also losing human interactions, right? Like a lot of times I feel when we don't see each other, you know, because I can't see you, I'm not sure if you're learning at each step or not, right? Because in the class I can, or any professor, we can look at you and see, you know, how you feel or if you're following or not. That's really the hard part here.
Mm-hmm. But I think people will notify you if we're actually if we actually don't understand something, or at least I would say something if I don't actually understand something and tell them that I don't know what's going on. So I think that's very important. Notify the teacher or or you for that matter, to like say if they don't know anything.
Yeah, that's pretty important. Yeah, that's pretty important. So yeah, so that's pretty important. So if there's something vague, you should definitely give me a message or just, you know, say something. Yeah, that's important. Okay, I'm trying to go as slow as possible. So in order to make sure you're all on the same page. Okay, let's continue. Okay, let's look at this function. Is it uniformly continuous or not? Do you have any answer?
Probably.
Probably. Why?
You're
right, it is uniform.
Yeah, the difference is that on the previous interval, we went all the way to 0, and there's, I mean, there's an asymptote there, and there's no asymptote, vertical asymptote here.
Yeah, that's very clever. Yeah, so as I mentioned in the previous solution, the reason why it's not uniformly continuous is because sometimes you have nearby points, and if we look at the value of the functions, they're close to each other. Sometimes we look at nearby points, but when we look at the value of the functions there, they're not close to each other anymore. And as we're getting closer and closer to 0, the situation will get worse and worse. But not here. The definition of the function, the domain of the function, doesn't allow us to go to 0. So even in the proof, at certain point, we end up with an inequality, and I took the limit and I sent the x to 0. Here, I can't do that anymore. So it makes sense to guess that the function is uniformly continuous, and it is indeed the case. So in order just to prove it, I want to prove it rigorously. I should show for any epsilon, there exists delta, such that if x and x prime are closer than delta, then f of x and f of x prime are closer than epsilon. But here, the point is that x and x prime are in domain, which means they're in the interval from 1 to infinity. They can't be less than 1 anymore. Okay, so suppose epsilon is given. That's the way we should prove it. I need to find delta. So I need to find delta such that if this condition holds, x and x prime are closer than delta, then this condition would hold. Now the trick is that we should start from here. We should start from f of x minus f of x prime. F of x minus f of x prime is 1 over x minus 1 over x prime. We want this to be less than epsilon. This is what we want. Right, okay. So we want x prime, x minus x prime to be less than epsilon, which means we want x minus x prime to be less than epsilon x prime, correct? Now, this is the difference between x and x prime. This is something like delta, right? Or it is, say, it's less than delta. And we want epsilon x prime to be larger than this quantity. Or in other words, we want x and x prime to be so close to each other such that this thing holds. So if x and x prime, okay, wait a second. If sorry, a technical difficulty. Let me. Okay, so we want to have, so the thing we want to have is that we want x minus x prime to be less than epsilon x prime. This is what we want to have. But we know x minus x prime are supposed to be less than delta. it's supposed to be the condition, right? This is how we are supposed to choose x and x prime. So if delta itself is less than epsilon x x prime, then it would be fine, right? So if delta is less than that, because x minus x prime is less than delta, if this is also correct, if delta is less than epsilon x x prime, then of course x minus x prime would be less than epsilon x x prime, which, as we saw in the previous page, it means it's equivalent to 1 over x minus 1 over x prime being less than epsilon. So the only thing which remains to be seen is this thing, circled with blue line. So we should choose, okay, we have some difficulty here, unfortunately. We should choose delta such that delta is less than epsilon x x prime. Okay. Oh, you're confused. Which part? Did you follow how we got to this condition? Delta less than epsilon x x prime.
Wouldn't delta have to be bigger than epsilon x x prime if we're given that if we know that x minus x prime is less than epsilon x x prime, and we're trying to prove the second line there? So would delta have to be bigger
Okay,
then?
let's go. Let me see if we can go back to the previous page. I'm not sure if maybe I shouldn't have erased that. Sorry. So okay, look here. What we want is to satisfy the condition, this condition, 1 over x minus 1 over x prime being less than epsilon. Do you agree?
Oh, okay. So what we know is that x minus x prime is less than delta, and we're trying to...
But we are not sure what delta is good enough. So
Okay.
I want to find the good delta. That's the idea, right? I want to say for any epsilon, there exists some delta. I want to find this delta, okay? So we are assuming x minus x prime is less than delta, and then we are trying to use that as a way to find what delta really is. Okay. And the trick is always to start from this thing, f of x minus f of x prime is less than epsilon, and kind of trying to go back. So what we want is f of x minus f of x prime being less than epsilon, which means 1 over x minus 1 over x prime being less than epsilon, right? That's what we want.
Okay.
Which means x minus x prime over x prime being less than epsilon, which means x minus x prime epsilon x prime being less than epsilon x prime. Right, this is the condition we have. So this is what we have. We want to do that. And I said, because we know x minus x prime is less than some delta, which we want to find that delta. If delta itself is less than epsilon x prime, then everything's good. Because x minus x prime would be less than delta. Delta itself is less than epsilon x prime. Therefore, x minus x prime would be less than epsilon x prime. So if we have this thing, everything would be fine. Okay, I want to choose that as delta. So what is I want delta to be less than this thing. What is the minimum amount of the right-hand side? I want delta to be smaller than epsilon x prime for every x and x prime. What is the least value of the right-hand side? Remember, x and x prime are in the interval from 1 to infinity. Yes. So because x and x prime are in this interval, it means they're larger than 1, right? Both of them. X is larger than 1, x prime is larger than 1, therefore x prime is larger than 1. So x prime, so x prime is, let me erase this. So x times x prime, they're both larger than 1. So their multiplication is larger than 1. So epsilon x prime is larger than epsilon times 1. So if delta is less than epsilon times 1, which is epsilon, delta is less than epsilon x prime for all x and x prime in this interval. So delta should be less than epsilon. We can just choose, for example, we can choose anything we want. We can choose delta to be epsilon over 2. This is less than epsilon. And if we choose delta to be this thing, then we have this condition that delta is less than epsilon x prime, therefore x minus x prime is less than epsilon x prime. So if delta is less than epsilon over 2, delta is less than epsilon, therefore this red thing is correct. Therefore this condition is correct. Therefore f of x minus f of x prime is less than epsilon, which is what we were looking for. Okay, any question?
Yeah, I have a question.
Yeah.
So if you have a vertical asymptote the way you do for 1 over x, will the function, so does that automatically mean the function cannot be uniformly continuous at that point?
Yeah.
Okay.
Yeah, that is correct. And here, that was the idea. Actually, we kind of removed the part which is asymptotically going to infinity. Yes, you're right.
Other questions. So are there other times when we know, like, it sort of will tell you that a function is not uniformly continuous in the same way as vertical asymptote would?
Yeah, I mean, there is no general rule as much as I know. So for example, look at f of x equals x. It is uniformly continuous. Because if I choose 2 points here close to each other, the value of the function for them will be close. Doesn't matter where should I choose these points. If I choose these 2 points here, the same thing would hold, right? But think, for example, about f of x equals x squared, which looks like this. If I choose 2 points here, the value of f of x would be close. If I choose the same, with the 2 points with the same distance here, value of f at one of them would be here, the other one would be, for example, there. And they are not close anymore. And x squared is not asymptotic, right? Yeah, so the point is that if the function is really growing fast, not asymptotically, this is not the asymptotic growth for quadratic functions. But in some sense, if the growth is not controlled, if you can't control the growth of the function, it usually means it's not uniformly continuous. This is a correct intuition to have. So sometimes we bound the interval. So for example, if I've told you x squared from, say, 0 to 100, then it would have been uniformly continuous, because on this specific interval, the growth is bounded, right? But if you let the x becomes larger and larger, we can't control the growth of the function. The growth becomes faster and faster. Yeah, this is correct. Okay, okay, so it needs to not grow faster than a constant rate.
So the growth needs to be bounded by a constant a linear function in a way? So like that there is like a, I don't know,
yeah, I mean,
a slope that
well, what you're saying again intuitively makes sense, but this, I guess it makes sense when the growth really makes sense when we are going to infinity. But as you saw earlier, it can only happen at a point 2, like 1 over x, right? So in some sense, you're right, but we don't usually use the word growth for that. But yeah.
Okay. Yeah, that wasn't the best way to express it, but.
Yeah, but you're right. If it's going to infinity, yes.
Okay.
We should be able to bound it. We should be able to bound f of x minus f of x prime with x minus x prime. And that means in some sense, so, well, I'm not completely sure about things I'm saying, but in some sense, we have this quantity and we want to bound this quantity with x minus x prime, right? So in some sense, this is delta, this is epsilon. We want to control epsilon using delta. And in some sense, it means f of x minus f of x prime over x minus x prime. This quantity shouldn't be very big. We should be able to control this quantity. And this is if the function at least is differentiable, this is derivative of function at some point. So it means we should have a bound for the derivative of the function. If the derivative of function is getting bigger and bigger and we can't bound the derivative, for example, that means it's not uniformly continuous. Yeah. Okay, so the next question is quite simple question, actually. The question is that is multiplication of 2 strictly increasing functions and increasing function? Think for a minute. It's a simple question. No, we don't have any assumption on the functions. They can be positive, negative, or something else. And not if one is negative and increasing. Yes, you're right. So can you give me an explicit example? Okay, let's see. X squared. So f of x equals x squared. And g of x equals -1 over x. So x squared is, well, you mean for when x is positive, right? Say x is greater than 0. So in that interval, x squared is increasing. And -1 over x is also like that. It is also increasing. Their multiplication is minus x, which is like that, which is decreasing. Yeah, that is correct. That is definitely correct. So another example, which also works everywhere, if f of x is just x and g of x is, say, x minus 1, both of them are increasing functions everywhere. F of x equals x is this one. F of x equals x minus 1 is this one. Their multiplication is x times x minus 1, which is x squared minus x, is like this. Of course, it is not increasing function. Sometimes it's increasing, sometimes it's decreasing. Okay. So that's it. For the third question, I'm asking, consider this function f of x to be x squared if x is rational, and 0 if x is not rational. I'm asking, is f continuous at 0? If yes, is f differentiable at 0 or not? So in some sense, we can think about the graph of the function. You know, you can think about the kind of rational numbers in the set of real numbers. There are countably many, infinitely many rational numbers. There are countable subset. At those points, we would have x squared. So the graph of the function over q over rational numbers would be something like this. At irrational numbers, the function becomes like this. There are infinitely many irrational numbers. They're uncountable. And the point is that the function, the 0 and 0 is the point of the function. The question is that if the function is continuous at 0. The answer is simple, yes or no? Yes, because when x goes to 0, f of x would also go to 0. The first thing to note is that the value of the function at 0 is 0, right? Because 0 is a rational number. Therefore, the value of the function at 0 would be 0 squared, which is 0. Now, it would be continuous if the limit of the function, f of x, when x goes to 0 is equal to this number f of 0, which is 0. But that's the case, because when x goes to 0, doesn't matter if x is rational or irrational. If it's rational, we should take limit of x squared when x goes to 0. If it's irrational, it's just 0. If it's a combination of points in q and qc, it still doesn't matter. When x goes to 0, doesn't matter if you go towards 0 on using the red graph or blue graph. Anyway, the function would converge to 0. Therefore, it is continuous. But more challenging question is that if the function is differentiable at 0. So the answer to the first question is yes. What about the second question? Is the function differentiable at 0? Does it look differentiable? Are you telling me, Kyle, or you're asking me? My guess is yes. Yeah, I think you're right. Let's write the definition. You're right. Your intuition. Since x squared and 0's derivatives agree at 0. Oh, yeah, that is the correct answer. So let me write it down. When we want to see if a function is differentiable at a point or not, we should always use the definition of derivative. We want to see if f prime at 0 exists or not. Let's write what it means. It means limit of f of x minus f of 0 over x minus 0 when x goes to 0, right? So it's limit of f of x over x when x goes to 0. Does this limit exist? Well, we know there are two cases for f of x. It's either x squared or it's 0, right? When x is converging to 0 at each point, depending on whether if x is rational or irrational, f of x is either x squared or 0. In the first case, we get x squared over x, right? Which is just x. In the second case, we get 0. When x goes to 0, both of these things converge to 0. Well, constant 0 is 0, and in the first case, x squared over x, which is x. When this one converges to 0, we still get 0. So the limit is 0 no matter what, exactly because of the reason I think Kyle mentioned, because the derivative of both of the functions agree at 0. Therefore, it is 0. Yeah, that's it. And let's solve another question. Prove for any x and y, the absolute value of sine of x minus sine of y is less or equal than x minus y. You can just tell me why this one is correct. Just a word. Do you remember mean value inequality? Mean value inequality says if f is differentiable, f of x minus f of y over x minus y, this is equal to, so say this is the function f. If you choose a point x and a point y. If you look at f of x minus f of y over x minus y, it means, well, maybe my graph is not a good graph. Let's draw another one. It means look at this line segment here we have connecting the point x and f of x to y and f of y. This ratio fx minus fy over x minus y is equal to, it has a geometric meaning. What does it mean? I guess you know it. It's related to this line segment. What does this graph represent? Yes, the slope of this line. The slope of that segment we have there. And mean value inequality says if the function is differentiable, there exists some point c there, which if you look at the derivative of the function at that point, these two are going to be equal. Are you familiar with this? Are you familiar with this theorem? Have you seen this theorem before? If not, we can discuss this theorem more next time. But just that's the case. So for example, for any x and y, sine of x minus sine of y over x minus y is sine of x minus sine of y over x minus y is derivative of sine at some point c. But derivative of sine is cosine. And the absolute value of what we have here is absolute value of cosine, which is always less or equal than 1. Therefore, sine of x minus sine of y is less or equal than x minus y times 1. Okay, that's it for today. I should actually get to my next class. Yep, think about these, and if you have any question, you can just email it to me, okay? Stay safe, stay healthy, stay home. Bye.